a section where we can go through and do some demos. Encourage people to kind of, think of things you can show. You don't have to do a huge amount of preparation for this, but it'd be cool to just see what people are doing with Dask, how people are using things. And Doug, you have offered to give us a demo. So do you want to take over the screen share and take it away?
Yeah, happy to. Thanks so much. Yeah, let me get this going. Is that visible? Oh, that's the meeting notes. Here we go. Is that visible and legible to people? Can you read the text okay?
It looks good to me.
Okay, awesome. So hi everyone, my name is Doug Branton. I am a software engineer with LINCC Frameworks. There's a number of us here in the call today from LINCC. We have been working on top of Dask for 1 to 2 years now with applications in astronomy. And so I wanted to share this with you all for 2 reasons. I think one, to kind of show you an example of what we've been doing, but also we're very interested in kind of mining your expertise with some of the scale challenges that we have as well. So we have 2 packages that I wanted to kind of briefly cover today. But before that, I just wanted to give sort of a contextual overview of what LINCC Frameworks is. The LINCC Frameworks project is philanthropically supported by Schmidt Sciences. We're focused on developing scalable software within the field of astronomy. We have a more particular goal at the moment, which is that the upcoming Rubin Observatory, which will start taking data next year, is going to be providing on the order of like 20 petabyte processed catalog data set for the community. So this is a kind of new frontier for the field computationally. It's a larger data scale than what has traditionally been used before. And so as a result, this introduces a new computational demand to the science that people want to do with the data. And so the workflows that scientists want to employ and the tools that they're using need to be much more powerful while still being approachable, because these are scientists by training and not necessarily computer scientists or programmers by training. So that's really kind of our mission statement, is developing these approachable, scalable tools within astronomy with a specific goal of enabling science with this new kind of revolutionary telescope. So we have 2 projects that we've been building on top of Dask that are in our portfolio, one of which is called the Large Survey Database, LSDB, and the other is called Nested Dask. So LSDB is a framework for spatial analysis of extremely large astronomical surveys. So LSDB has the notion of a catalog class, which is built on top of Dask's data frame class. So we can read in a catalog. Here is our first kind of example code from data from the Zwicky Transient Facility, which is another observatory like the Rubin Observatory. So we can just read this in. This is a read hipscat call. It's effectively a read parquet call within Dask. And we can see what we've read in. And this is a Dask data frame for all intents and purposes. Now, where LSDB, one of the main points it differs is that LSDB has a more special partitioning structure employed called hipscat, or that name is actually subject to change and might change very soon. The idea being that pixels are defined hierarchically on the sky, aka a sphere. So each pixel on the sky is meant to contain roughly the same amount of data. So if we were to actually plot the distribution of pixels, you can see that the size of the pixel here is a measurement of density. So this arch that we have is actually the Milky Way, where there's a much higher density of things that we can see. And so there are many more pixels in that arch. The pixels are smaller size, density-wise. And so with Dask, this is actually that saying, instead of pixels, you would say partitions, because Dask partitions are the things that are holding this data. So we're making use of Dask partitionings as kind of the back end for this pixel distribution system that we're using spatially. Now, LSDB as a package is focused on large-scale analytics. So things like doing spatial filtering, data analysis, and then more of a custom use case in cross-matching, which is effectively a join between two catalogs where you don't necessarily have some sort of key to match on, and you rather would need to match these things spatially. So we can just walk through a brief example of that. So we can look at the data that we were using before, this ZTF table, but this time we can read it in using a search filter. So we define like a cone search, so a spatial cone on the sky that we can search through. This is all actually done pre-Dask, so we avoid submitting an initial graph that considers all of the partitions, and rather it's just what's defined in the narrow set of partitions meeting the search filter. And so this is a really small chunk of data. It's just two partitions. And our new map, when we take a look at it, is just two little pixels off to the side here. Now we can pull in another survey called Gaia and give it the same search filter, which is also two partitions with 2 pixels. And the ordering is slightly different. So one is sized larger than the other because different catalogs generally have different depths and densities. So we can cross-match these with a catalog custom function called cross-match. So ZTF object.crossmatch Gaia object with some additional kwargs. And we get a resulting table of matched things positionally with fields from both. So it's effectively a join. And we can compute this. Again, this is built on top of Dask. LSDB is not a direct, it leverages Dask and wraps it. And so all of the API things brought in are brought intentionally, but very much the same API is in place with LSDB. The other package I'd like to talk about briefly is nested Dask. Nested Dask is all about nesting pandas and Dask data frames. It's very heavily motivated by use cases we have in the field, but the package itself is not actually astronomy specific. It could be applied to many other domains besides astronomy. So to kind of showcase what nested Dask is, again, very briefly, we can actually start from the same place in terms of loading data through LSDB. So we load our ZTF object catalog just as you did before with a very narrow cone search. And we can just peek at the data here where each object has some spatial information as determined by these RA, right ascension, and declination columns. And then we have some additional things like an object ID. So this is a unique thing for each, a unique identifier for each thing in the sky, and some other characteristics. But this time, we can load in an additional catalog also from ZTF, which we call a source catalog, where sources are individual observations of things in the sky. So if you have an observatory which is measuring the same patch of sky repeatedly throughout time, then you're building up many sources over time to one object. So it's a many-to-one relationship between sources and objects. So the sources, if we're to load this in using the same filter and peek at it, it's a different table where we also have things like MJD. This is effectively a time of observation. MAG, which is like our intensity, band being like the photometric band that it was observed in. And we also have this shared key object ID, but you'll notice here that it's repeated. So these are 5 observations of the same thing. And in fact, this key that ends in 6866 actually maps to the first object. So these are the first 5 observations of the first object. Now, when I said that LSDB was built on top of Dask, I was not being precise, and that LSDB is actually now built on top of nested Dask and its nested frame object, which in turn is built on top of Dask's data frame object. So the type of the data frame itself here is what we call a nested frame. So with nested frames, we can nest data frames within other data frames by some shared column or index value. And so we can use this ZTF object.join nested ZTF source using that shared key of Pansar's or PS1 object ID and give it some output column name of light curve. And we get a new data frame that looks like our original object data frame, but it has this new column light curve with kind of a gnarly D type at the moment. which is a custom nested D type. So if we were to take a look at this to see what's going on, we can peek at the first 100. This is just the computed thing. So you'll see something that doesn't give you much more insight by looking at the values of this. But we can actually look at the first row with iloc 0, and then look at the value of light curve. And this is in itself a data frame. And so the value of this cell is a data frame of information. And all of the rows of this are all of the things in our source table that we loaded in that were matched to our object table by ID. So each object has its own personal data frame of all of the sources tied to it. And we call this kind of a light curve in time domain applications where we're looking at measurements in time of an object. So the nested pandas, nested Dask packages are all about actually working with data in this format. So this is kind of a one cell example, and there's a lot more that can be shown on this. But in this example, we would do something like a query, and this is showing off how nested pandas actually augments pandas and Dask's query function, where you're able to do something like this, where you say lightCurve.cat flags. What this is effectively doing is you can use query on nested layers. And so this query is targeting the data frames within the light curve column. And it's saying this cat flags column, which is the last thing here, filter these by this value equal to 0. Contextually, this is cleaning bad data from the data set as determined by these flags. But this is allowing you to work within the data frame context just one level deeper at this nested level. And the other kind of core thing that we think about a lot is our users and astronomers really want to apply data to light curves, or apply data to, or apply their custom workflows and functions to this nested data. And so we have a custom function called reduce, which is very similar to pandas and Dask apply, which allows you to apply functions while pulling in data from these nested structures as arrays to send to the function. So the example here, I can define a really simple toy function called myMean, which takes in a column called mag and takes the mean of that mag. So it takes the mean of an array that is called mag. And I can apply that through reduce with this lightCurve.mag. And this is this column dot subcolumn syntax is the same as above, where we're saying for each object, package the magnitude subcolumn of the light curve column into an array to send to that function. And so we get out a result here, which is the magnitude, the mean magnitude for each object. Now, I wanted to end this by putting some of our scalability challenges in front of you. We're very interested in very large scales of data, and particularly how you would think about this problem as more core Dask developers. And there's really two problems, primarily. The first is very large task graphs. So these full catalogs can have many partitions, especially source catalogs. So when for example, when I load in ZTF, which is a fraction of what Rubin will be, it's almost 42,000 partitions worth of data. Furthermore, the workflows that scientists are applying to this data are not always simple. Sometimes they can be messy, more involved. And so you can get very large task graphs that result from this. And so, we've read like Dask best practices, and they say generally you want to avoid this. But really, how do you avoid this? We've had some success with chunking type approaches, but is there anything else that we can be doing to kind of make this? And the particular failure mode is that these, the graph construction can take a long time, on the order of hours in some cases where workers are idling, or in some cases, maybe the actual graph never finishes constructing, right? The other big thing is worker memory issues. Workers running out of memory and dying is a pretty common occurrence in a lot of our testing. I think that there's what we're seeing a lot is that workers often need a significant amount of memory compared to what our intuition of the memory cost of the task would be. And so if we're dealing with that, the users that are going to be mainly responsible for making their own workflows and allocating their own computing sources are certainly going to have issues with this intuition problem. And safeguard measures like disk spillage don't really seem to work when you're using a more involved cluster setup. So again, I wanted to see if people had immediate thoughts or reactions to these, but that's basically all that I have. If you're interested in any of these packages, I've included some links here, and I've included my GitHub here, which is also in the notes. But thank you very much for giving us this time. And yeah.
Yeah, that's great. Thanks for coming along and sharing that.
No problem.
Really interesting. I'm interested in some of these things about, disk spilling not working on big clusters. Like it would be useful to see examples of when this is happening, and it's not something I would expect to happen. For example, we run big clusters and spilling happens.
Yeah,
and yeah,
mhm.
no, go on.
Yeah, I think one of the actions items for here, either in a separate meeting or, if issues are better for the Dask people, for us to maybe file some use cases and failure modes that we're seeing. I don't know what would be preferable to you all.
I mean, that'd be great. Like use cases are always helpful, and then some way that we can see the issue for ourselves is the key thing to being able to dig into it, right?
Yeah, definitely.
Is this is the source code for nested Dask open source?
Yeah, all three packages are open source and available on GitHub, and I can post some links in the chat.
A
I
couple-
just put
a couple
link
of questions
to Zoom chat.
Oh.
I will copy paste it from there. Sorry.
Thanks so much.
Great. A couple questions I have like immediately are like, have you run into any problems with like Dask expressions? Like, so Dask data frame now uses a different default, and are you using that new default or are you opting out?
Yeah, so all of our packages are using Dask expressions. Nested pandas and nested Dask were relatively recent packages that we've added, so they were actually all post expressions. LSDB, which I'm not personally a developer for, so others might be able to say more, I know had some issues implementing expressions, and for a time we're using legacy data frames. I think some of that boiled down to support for sort of delayed functionality. I think there were some data transformation issues happening at the delayed level. Yeah, if anyone's here from LSDB that knows more, like feel free to speak up.
I'll add a bit. So yeah, a while ago, Sean McGuire, who's our another software engineer, he posted a few issues about, and I think Melissa Duluc also posted a few issues about Dask expressions, that these two delayed became significantly slower. I'm personally a project scientist, so I'm from, user, could tell from user perspective. What I noticed, for example, when we switched from legacy data frames to expressions, that in one of my workflows, to-parquet call, just, previously it spent a few minutes on this lazy part before really starting to do, Dask tasks, right? Before anything appears in the dashboard. And now it spends something like 20-30 minutes on the same code, right? Just for this lazy part. So before even doing something just for scheduling. As in Doug said, right, we have these problems with very slow scheduling, if I use the right terminology. Sorry if I not.
That's interesting. Would you actually have a link to an issue like that? For context, I've also literally Monday or so fixed one issue that was delayed to graph submission, graph generation. In that case with from delayed calls. But yeah, if you have an issue for that, might be something I could at least take a look at and see if it's similar.
This definitely sounds
I
like something would be good to dig into. I wonder if we should continue with like the agenda of the meeting and we can add this to like something to circle back to at the end.
Sure.
But it'd be cool to dig deeper into these and see what's going on. Does anybody else have any questions about the demo?
Well, just quickly, and we can go into details like you said later. Do these file formats allow for partial I/O, or do you need to kind of read in the entire file and then filter out the information you need?
So it's all Parquet in our use
Oh, great.
cases,
Okay.
so it's columnar, yeah. And then like I mentioned,
you did mention that.
Yeah, as well, like we do have filtering that can happen pre-Dask. So you can only sort of submit a Dask graph for a subset of partitions when you have massive file sets as well.
Cool, awesome. Any more questions before we move on? Perfect. Okay, thanks again for coming along and doing that demo. That was great to see. I was also hoping to do like a quick little Dask job queue demo, which is just the demo that I did in my talk at EuroSciPy for folks that might be interested in that one. This is going to be like an off the, on the fly demo based on I did something last week and I can just about remember how it works. So let's just go through and show some things, but this will be a minute or two. So hopefully everybody can see my screen. Shout if you can't. If you've used Dask job queue before, it's a tool for submitting Dask clusters onto HPCs via various job schedulers. I have Slurm set up on a machine just for like developing and playing around with this demo. So I'm just going to do, if I just watch the queue, you can kind of see some of the things that's going on. So if I just start an IPython shell, the way things would typically work in Dask job queue is if I do from Dask job queue, my autocomplete is probably going to give away half this demo. But if I import a Slurm cluster from here and create a cluster like this, I can see that I've created this cluster. Now, maybe actually to start this, I'm just going to come back out of here. I'm on my machine at the moment, but typically you would be getting some kind of interactive shell into the HPC in various ways. You might have Jupyter Hub giving you Jupyter sessions. You might do something like srun-n1 IPython like this. You can see in my queue now, I've got one allocation. I've grabbed a node on that machine. I'm now interactively on that machine. And if I just create my cluster again. Now in this situation, my IPython session and my Dask scheduler are on this node. But now if I want any more workers, I can do cluster.scale, and it will submit more jobs to Slurm, right? And if I scale up to 1,000, it will submit 1,000 jobs. And this is great. It can auto scale, it can move up and down. I can run work on this and do whatever I like. So let's do from distributed, import a couple of things, and let's import, let's create a client next. And then if I do import Dask array, I'll create an array, a big random array, and then do that. Yeah, I can like calculate the mean of a big array. And if I persist this, then I could watch the progress of that future. And, the Dask cluster is chugging away on those workers doing that thing. This is all very interactive. This is very nice. If my workload is varying in kind of demand, it can be dynamically adding and removing workers. This is great. And it works well in situations where maybe you have an HPC system that prioritizes small jobs or has lots of gaps in the scheduler. And so Slurm can do some backfilling and putting workers into little gaps. And this is a very traditional way to use Dask job queue. But we often see folks running into problems where they get told off for submitting loads of jobs like this, or they would prefer to submit one big job that's got all of these workers in. They know, oh yeah, I want 100 workers or 1,000 workers, and it's going to run for 20 minutes, and I just want to submit that as a thing, and then Slurm can schedule that like you would with any other kind of HPC thing. So this is where the runners come in, and if I just exit out of this, all my jobs should free up. The new class we can use is this runner class. And if I just make a new file for this, I can do like from dash job queue, .slurm, import Slurm runner. And then I can do something like with Slurm runner. That's runner. This is not like using a cluster. Let's just import from Dask distributed client. So I could say with client runner as client. Okay, and then I might want to put some Dask things in here. So maybe I want to do the same thing. Maybe I want to do, let's get progress from here as well. And then import Dask.array. And then if I do the same thing, da.random. This is just like default values that I have stored in my brain for doing demos like this. Maybe this will work. It's probably a good size. And then if I do like O equals r.mean, persist, and progress on O. Yeah, so I have this like one script now. Go on, Matt.
The file you have to do as DA for import dask.array.
Oh, thank you. Bit live coding. Yeah, that looks roughly okay. So this is basically the same as what I did before, right? I've created a Dask cluster, I've imported Dask array, I've done a thing, but this is all contained in one script, and I've got a context manager that sets things up. And what I'm now going to do is submit this to Slurm as like a, I want 100 nodes or whatever, and it's going to run this script on every node. And this Slurm runner class kind of does some clever communication between all of the nodes to decide, okay, who's going to run the scheduler, who's going to run the worker, who's going to run the rest of this context manager, and they kind of set all of that up. And now if I do like srun and or like that, I should see Dask startup. Oh, what did I do wrong? Chunk. It's chunks, isn't it? Okay, so we're kind of getting the, oh, I typed it badly again. What did I do? Right. I did do this earlier so that I could screw this up and it wouldn't matter. Okay, that's that same code but without a typo in it. This is showing me the output from all of the nodes I've got. You can see at the bottom I've got like one job that I've submitted. I've said I want 4 nodes. One of them decides to be the scheduler. It starts the scheduler. It broadcasts its IP address. Some of them decide to be workers. They connect. One of them decides to be the client. It runs what was within that context manager, and you can see it's the same code, and we're seeing the progress and everything. So if you want to run really big jobs, we're doing this at NVIDIA on like some projects like Nemo and things where we want to run like a big GPU cluster, and we know what we want to run, and we just want to submit some workload. This is quite nice if you want to just write one script and then run it kind of at scale on an HPC using Dask. So that's the whole demo of that, but that's what's new in dask-joqueue recently. Does anybody have any questions about that?
If I could ask as a joqueue user, and Slurm clusters there as well. So how do they know how to communicate? What if you run two jobs like that, right? What would happen?
So in this situation, I left all the defaults on just to make it look super smooth, but that Slurm runner class takes a scheduler file optional keyword argument, and it will create a file on the shared file system with the ID of the Slurm job that gets submitted. And so it's using the shared file system to communicate, basically. It's assuming that wherever I am running from is the shared file system in the default, and it just tries to write it in the current directory. But you would probably put, like path to my shared file system, creates a scheduler file. You can submit loads of these. It uses the Slurm job ID to make sure that they don't crosstalk or anything.
Great, thank you.
I would love for them to actually use PMI to do this instead. But I went very deep down the rabbit hole of like pure Python PMI implementations, which is a deep hole. There's nothing you can install from PyPI that will give you this out of the box. And the PMI X package does have some Python stuff, but it's hard to get it in your environment. And yeah, it would be nice to do things without the shared file system, but yeah, maybe one day. I also do have an MPI implementation of this, but it's nice to do things without invoking all of MPI. We find in GPU stuff that just importing MPI for Pi has consequences in other libraries. So trying to avoid that in places. But I think that's it for demos.